Okay, welcome back, folks. So what does it mean when we say magnet? Where is magnetic property of a magnet coming from? Why similar pole repelling? Where is it coming from, right? So it was obvious, oh, magnet exists naturally there, so you can find those magnets. So that would be the answer. But the question arises, why can't we separate North and South Pole? Why cannot we do that? Why cannot we have monopole? Okay, so to answer that question, we need to go back and look at the origin, where the magnet comes from, magnetic property comes from. Okay, and it turns out that magnetic property of a material arises from the motion of electron around the positive charge. So it comes from the motion of charges. So that means motion of charge means current. So basically it arises from the current. So even when we are breaking a magnet, what's happening? We are not breaking an atom. So as long as atom is there, it's going to have two poles. And how we determine the pole of the, pole of the magnetic field generated from a current, we're going to be talking about that pretty soon. But for now, let's just keep in mind that, okay, it comes from the current, and current can produce magnets, okay? Or I should say magnetic field rather than physical magnet. It can produce magnetic field that can act like a magnet, okay? So in this drawing, that's what I'm trying to show you. So for example, there is a positive charge here, and an electron is orbiting around it. So because of that, what happens? The motion of the charge is current, so the flowing current is generating a magnetic field that's going like this in a loop. So what happens? It goes in a loop. So for the charge and electric field, what happened? What was the case? So if it was positive charge, any field generated from the positive charge just went straight, right? But the magnetic field, they have to loop and come back because it originates from a motion of a single charge. It can originate from there, okay? So now, any material, that is the combination of several such atoms, and each atom has so many electrons. So if one electron is going clockwise and another one is going counterclockwise, they generate magnetic field in opposite direction and they cancel. So that's why not every materials are magnetic. But some materials can be magnetic, can be made a magnet. For example, iron can be made into, let's say, magnet. So how does that happen? Because for the iron, there are these orientation of the electron that, like the tiny magnet, let's say, that originates from a single electron. What happens? All of them, they don't cancel, okay? So what happens is there is certain lineup in a certain region, okay? So those are called magnetic domain. So if they are randomly pointing with each other, then there is no magnet, there is cancels. But if they are lined up a little bit like this, then that generates the magnet. So if we bring those tiny magnet, and remember they are there, near another big magnetic field, what happens? This big magnetic field forces those tiny magnets in the same direction. So that's how it becomes kind of a magnetic. So I think I don't have it here, but let's say if you have, let's say you have some sort of magnet, not magnet, yeah, a magnet and a magnetic material like iron. So usually it works just fine if you have clip, iron clip, right? The paper clip we use. So make it straight. and then bring one pole of magnet and then drop something like this. Go from one side to another side and then bring it back. So don't go back and forth. If you do that, then you are just doing randomly. So those tiny magnets are going this way and that way, this way and that way. So you are not lining them up. But if you just go in one direction and come back and do the same thing repeatedly, if you do several times, that tiny nail or the paper clip kind of becomes magnetic. Okay, so you can create or make a magnet. So that's the process. So that's what the bar magnets are. That's what the solid magnets are. They are just, they are these tiny, tiny magnet line up, net magnets. They are lined up in a particular direction. That's what that is, okay? If you hit them, what happens? They become random. So the magnet loses magnetic property. If you drop them, what happens? They can be randomized again because of that vibration or force. And because of that, it may lose the magnetic property. Okay. So anyway, and so that's the magnetic material and the magnets. But remember, origin of all magnet is from the moving charge or current. And that's what we're going to be talking here. Okay. So when we make, we can make electromagnet. That means magnet from the electric current that flows through a coil like this. Okay. And the magnetic field is just like the magnetic field of a bar magnet. You can do that. Okay. So you pass current through the coil. What happens? It has magnetic field lines just like a magnetic field of a bar magnet. So this is called electromagnets. Probably, I don't know if you have seen, but in some places where there are like a garbage thingy, and if they want to separate metals, let's say iron objects from the pile of garbage, what they do is they bring huge electromagnet near that garbage pile, and for example, if there are iron and so on, they get stuck there, and they move the arm of that other side and turn off the current. Once there is no current here, what happens? They're not going to be magnetic field, means it doesn't work as a magnet anymore once you turn off the current, okay? So that's how the knowledge of this, electromagnetism can be used. And many devices, even the medical devices, for example, NMR machines and so on, imaging machine, different kind of machine that used to image, make image of your brain and so on. I'm not talking about X-ray machine, but the machine that acts like an X-ray but doesn't use the X-ray. Okay, so they also use magnet, and that magnet is generated by just circulating currents. So they are there everywhere. Okay. So now, magnet comes from moving charge. That means moving charge is current. So current means moving charge. So if there is a wire that has a current, means it has a moving charge. Now, if you bring another moving charge near it, then what happens is it experiences force, because this moving charge is generating a magnet, and this moving charge, another moving charge, is also generating a tiny magnet. So these two magnets are either attracting or repelling, something like that. So you can see that effect. And that's what this is. So here in this demo, you see magnet is being used to manipulate the let's say, electron, direction of motion of electron. But electrons are too tiny, we cannot see them. But if we put fluorescent then what happens is when electron moves through those tiny dust particle, they emit light. So that way we can see, oh, those light is coming from the moving electron. So that way we can tell, oh, that's where the electron are going. Just like if there is a dusty road very far and you are looking at from very far, you may see the cloud of dust is moving. You may not see the car moving there. But just by looking at the cloud of moving dust, you can tell, oh, there must be something that's making that cloud, and the cloud is moving, okay? So same idea here. So let's watch this video. And let me make sure I turn on the sound. I think there is sound here.
An electron gun and a...
So do you guys hear the sound?
Yeah.
Okay, great.
phosphor screen. The electron gun emits a beam of electrons which travel down the tube and strike the phosphor screen, which gives out light. So the blue dot on the screen shows you where the electrons are. We accelerate the electrons through a voltage difference of 1,000 volts, and they strike the screen with a velocity of 20,000 kilometers a second. That's the distance from Christchurch to London in 1 second. Here's the magnetic field. It's just a simple lab bar magnet with an arrow drawn to indicate the direction of the North Pole. So I have field lines coming out of the North Pole, looping round and coming back into the South Pole. Now watch what happens when I bring the magnetic field close to the beam of electrons. You can see that there's a force on the electron beam downwards, and the force is at right angles both to the...
Yeah, pay attention that right angle, 90 degrees. See how it's 90 degree. Electron is moving 90 degree compared to the motion of the magnet.
magnetic field and to the direction of the electrons. And if I bring the magnetic field down from the top, the electron beam is deflected to the side. And it doesn't matter what angle I bring the field, the electron beam is always deflected at right angles. So it's really important that the magnetic field is at right angles to the direction that the electrons are traveling. If I bring the field along the same direction that the electrons are traveling, you can see that there is no deflection. You only have deflection if you have magnetic field at right angles.
Okay, so that was the video. So you have only magnetic field when they are 90 degree. Or I should say they're not going to be force if they are like 0 degree or 180 degree. At all other angle, there is force, but force is maximum when it's 90 degree. So now the question is, how do we write that equation? Okay, so how do we write that equation? So how can we write how much force is acting on this charge here because of this magnetic field? So it turns out, so it makes sense, okay, it may depend on the value of this charge, value of this magnetic field, and how fast it is moving, but also what direction it is moving. Okay, we need to keep that in mind. If it is moving in the same direction as a magnetic field, it does not generate. If it's moving exactly opposite 180, it does not. So we need to include all those thingy. So how do we do that? Let's take a look. So here, this is the force due to magnetic field. Remember, force due to electric field, force on charge due to electric field, we already learned that. That is Q times E. and the force is in the same direction as electric field if this, as long as this is positive charge, and if this charge is negative, then it's going to be in opposite direction to the field. Okay, so that we already know. Now what we are doing is we are trying to write the equation that gives us the magnitude and direction of force. What force? Magnetic force, or force due to magnetic field on moving charge. Okay, so that's what we are doing. So we are writing this. So Q, B, and B, and this sign may look like a regular multiplication sign, but it's a cross product, we call this. Okay, you don't have to worry too much about the cross product here, but if you are familiar with vector products, can be dot product and cross product. Yes, I haven't talked explicitly about those two different kind of vector product, and we don't need to worry too much about it, but we need to keep certain things in our mind to use it. For example, when we wrote the definition of work done, force times displacement, it was FD times cosine of angle between them. And I gave a lot of emphasis. If you took physics 1 with me, I gave a lot of emphasis that you always say this theta, read this theta, not just as a theta, but read this as an angle between force and displacement. Okay, so vectorially speaking, what are we doing is we are multiplying one vector force, another vector displacement, and what are we getting? We are getting work done, and work done is a scalar. So this kind of product is called dot product or a scalar product, okay? And I may not have mentioned it, but we used it. Now, what we have here is there is V vector, B vector, and we are multiplying B and B. And what are we getting? We are getting force, which is a vector. So when we multiply one vector with another vector and get another vector as a result, then this kind of product is called vector product or cross product. So when we have that, what do we get? Instead of cosine, we get sine, okay? And why that sine is relevant, why it works, okay? So for example, let's say in the demo we saw when field, magnetic field, in the direction of motion of V. So B and B, they had angle 180 degree. What we found, force was 0. Why? How did we know? Because the dot wasn't moving left or right when the guy brought this directly towards the magnetic field. Sorry, towards the direction of motion of the electron on the tube. Okay, it did not. But when it came sideways at 90 degree, when theta was 90 degree, the force was maximum. Force was maximum. So this is the property of sine. Sine function is 0 when angle is 0 or 180 degree. But it is maximum when sine is 90 degree. Sorry, the angle is 90 degree. Sine 90 is 1. That's the maximum value a sine can have. And either sine 0 or 180 degree, what happens? It's a 0. Sine 0 is 0, sine 180 is 0. So that tells us when angle is 0 or 180, this becomes 0, means force becomes 0. So that's how we are transforming our experimental observation into mathematical equation. So that way we don't need to keep on moving that magnet all the time. Rather, we can just look at the mathematical equation and tell what's going on, or can tell what's going to happen, okay? So that's the beauty of physics. You don't need to do experiment all the time. You do experiment and come up with the model, and you can use that model, okay? Or you do experiment to verify the model that you come theoretically. So here is giving us the value of the force due to magnetic field on a charged particle Q, okay? So that's what it is doing. So what is the angle here? So angle is between B and B, just like this angle here in the definition of work was the angle between force and displacement. Similarly, this angle is between B and B, okay? It's the angle between B and B. Now, the force being, if the force was scalar, for example, we did not care about the direction, then this would give us the magnitude and we would be just fine, happy camper, okay? But the problem is that the force has a direction. So now let's say you move a magnet in a particular direction, which way the electron gonna start moving, which way the charge gonna start moving because of the force, right? So just knowing magnitude not gonna be enough. You need direction as well. So finding direction is one extra step for us for this kind of situation. So magnitude, there is formula, you can use it, okay? As long as you are using it correctly, okay? So make sure to just use the values of Q, B, V, just the values, okay? Now, sine theta, so use the angle and use the angle that is less than 90 degrees. So for example, let's say if this is something like this, you do not want to go for this angle, rather you want to go for this angle, okay? Smaller among these two angles. Use that. So that means you are just using values here to get value. So now, how about direction? So force, negative or positive sign, gonna tell us about the direction of force, okay? So how do we find it, okay? So yes, one way, just keep track of the angle and plug that in and try to get it, but it may not be always so practical. So what we do is we make an extra effort to determining that, okay? So that's what we call a right-hand rule, and we're gonna be using that a lot. So here, this is another way of doing it. So for example, if I pair this B and sine theta, it looks like one of the component of velocity, okay? So what it means is when B becomes perpendicular, theta 90, that's what this symbol means, okay? 90 degree, but in short, we just use that symbol, okay? So when B is perpendicular to B, it's a 90, and sine 90 is 1. Means we don't need to worry about sine thingy. So that's when the force is maximum as well, because the maximum value of sine can have is 1, right? So that's that. When it's perpendicular, then you can just write Q, V, B. You don't need to worry about sine, because sine 90 is 1, right? But even if you were to write it down, you're going to get the same result, because if I write sine 90, then that's going to be that. So the B sine theta acts like a component of either velocity, or you can pair with the magnetic field if you like, and that's going to be component of magnetic field. So here I am dropping this V here as a perpendicular, or you can just drop B here perpendicular and find this component of B along the direction of B. Either way, it should be fine, okay? And we have done that while finding the work done as well, if you remember. I do not want to go back to that, but it's the same idea, okay? So that's what this means, okay? So now, when is force 0? There are situations, for example, if any one of these are zeros, then force is going to be 0. So that also means if B is not moving, force is 0. If there is no magnetic field, of course, they're not going to be force due to magnetic field. That makes sense as well, right? If there is no charge that's moving in a magnetic field, it's not going to experience any force. But if there is magnetic field and there is charge, then what are the scenario when, you know, the force becomes 0? 1, if the charge is not moving, B is 0, okay? So even if charge is moving, B is parallel to B. So they are in same direction, means theta is 0. Or anti-parallel, and we take that as a parallel as well, 180 degree, that's going to give 0 as well, okay? So that those are the situation when we get force 0. Now, what's the unit of magnetic field? Since we are introducing first time, so let's start from here. We know unit of force, we know unit of charge, we know unit of speed, and Coulomb is the unit of charge, but current is most fundamental. So we want to write in terms of current. So that's what I'm doing here. Okay, so just the magnitude of B is force divided by Q times V, and this for just finding the unit. So that means force, charge, and velocity, right? So if I want to go from charge to current, what I need to do? I need to divide charge by time, right? And time is sitting right there underneath this velocity. Velocity is displacement over time. So I can rewrite this equation, okay? So by doing that, what I did is I just wrote this velocity as distance over time. So it's a displacement over time, but we are just looking for the unit, so it doesn't matter. So that's why I'm writing distance, unit of distance and displacement, they are same, right? So now when I combine charge divided by time, that becomes current, right? And distance is meter and force is Newton. So from here, I can write that unit Newton. It's kind of a little bit blocked here in my view. I don't know about yours. This is the same thing here. So Newton and current means ampere, right? Unit of current is ampere. So it's just Newton over ampere times meter. So that's the unit of magnetic field. Looks very boring, complicated. So we give a name called Tesla. So that's what the Tesla is. Okay, 1 Tesla is Newton over 1 ampere times meter. Okay, so that's where the unit of magnetic field comes from. That's the SI unit. Okay, so that was about finding the magnitude. Now let's talk about finding the direction. So for that, you need to free up your right hand. See, it says right hand rule, and there are a couple of right hand rules. Okay, so that's why I'm writing this as a right hand rule number 1, but there is no, you know, a fixed mark. Like it's not like a Newton's first law, Newton's second law. It's not like that. Just for convenience, I'm, you know, saying that's the 1, okay? But we can just refer that as a right hand rule. So what does it say here? So to find direction of force, we can start by looking at this formula. And remember, this QB cross B is not equal to B cross QB. It's not. When we switch the side, in this case, for the vectors, what happens is you get negative of that, okay? So make sure you are writing like this, B first and then B, okay? B cross B. And we are just sticking key. Q is just a scalar quantity. We are just sticking with the V, okay? Pairing with the V, okay? So QV cross B. So now, so what's happening here? There is a magnetic field. Let's say there is magnetic field pointing this way, and there is charge moving this way. And first, let's start by talking in terms of positive charge. For the negative charge, it's going to be exactly opposite. So if we know what happens to the positive charge, we can tell what's going to happen to the negative. So let's keep positive charge first, okay? So So this is the direction of motion of this positive charge. So that's what I'm drawing here. And this angle could be any. But what has to be true is that they have to be in same plane, okay? So what it means, if B is in this plane, so you see this pen here, black pen, B has to be on the same plane. So that's that. So if this is sticking out, oh, hard to see, right? If it is sticking out from the plane in any other direction, we're not talking about that, okay? So if it was something like this, then we need to assume the plane is where both of them lie, okay? So for example, I think it's gonna be easier if I use my finger here, right? Okay, there is camera, right? So that's the plane here. Oh, it's blocked. Okay, now I think you can see it, right? So here, so this is plane, and these are B and B, let's say, okay? They are on same plane. If they are slightly tilted like this, and if your plane is like that, we're not talking about that. So we need to assume the plane is, you know, the both of them are lying on the same plane. Okay, so that's the first thingy. So that's what it is talking about. So now we want F, and F gonna be perpendicular to both of these now. Okay, so what it means, your B and B, they are in this plane, let's say, in this plane. Okay, so now what's the direction of F? The F is perpendicular to that. So perpendicular to the plane means this, right? So this could be pointing this way or other way around, opposite, okay? It could be pointing other way around. So now that's the problem, okay? If it was just one way, then wouldn't be any problem. But this could be, the force could be pointing, you know, perpendicular means either this way or that way, right? So how do we figure out exactly which way? So that's what we are learning here, and that's very important, okay? And I will be asking you a question about those in the test, right here in the clicker and so on, okay? So keep that in mind. So how do we do it? So I have listed that as few steps, okay? So just in case if you need help or if you forget, you can come back and look at it, okay? Stretch 4 fingers in the direction of V. So if there is V pointing this way, then you stretch these 4 fingers in the direction of V. If it is pointing this way, then you stretch that in that way, okay? And then what you do is now you crawl those 4 fingers. Oh, that's the stretch. Now you crawl them. So to crawl them, you need to know which way B is, okay? So you need to crawl such a way that you are about to grab the B magnetic field. So for example, here I have this and that. And now let's suppose my black pen is a magnetic field and this white one is, let's say, V. That's the direction of motion of positive charge. So I start by, you know, pointing this way. Now I crawl my fingers in the direction of this white pen here, in the direction of B, okay? So now my thumb is pointing this way, so that's the direction of force, okay? So that's the direction of force. Direction of force comes from this direction of thumb. When these fingers go from direction of V, I think I went from B to B. I'm sorry, that's opposite, okay? From B to B. So it's supposed to be B this, and this is B. My bad, sorry about that, okay? So could be already confusing, and I said opposite here, okay? So reset, let's reset everything, okay? So let's suppose this is the V and this is B. So you start by pointing in the direction to B, means white here, and crawl this towards the B, okay? So that means towards this black one there, okay? And doesn't matter what angle they have, okay? It doesn't matter. So if angle is small, it's still the calling direction gonna be same, okay? So now this being V and this being V, that's the direction of force, okay? So now what if it was like this when I talked about before, right? So you don't start from the direction of B, rather you start from the direction of V. So you start like this. If you do that, you cannot crawl your finger. See, you cannot crawl your finger this way, right? So what you have to do is you need to start with your palm flipped. So if I do this and line up in the direction of white pen, now I can crawl this in the direction of dark pen, okay? So now you see this is in pointing in opposite direction. Okay, this is now pointing in opposite direction. Thumb is pointing in opposite direction, means force is in opposite direction. So depending on if you switch the direction of A and B, direction of force changes. Okay, so that's how you do it. So these couple of steps you need to keep in your head. Okay, so now you can do this for the positive charge, and for the negative charge, it's going to be opposite. But if the direction of B for the negative charge is given, what you can do? Yes, you can assume that as a positive, find the direction for that assumed positive and reverse it, or you start from the opposite direction for the B, repeat that, okay? Either way is fine. So this one comes from the practice. Okay, I wish I was in the classroom and was working with you guys, okay, swaying my fingers, okay. Hope you guys watched and followed. And here is a test, okay. So if you learn it or not, okay. So you can see there is direction of B, this is direction of B. You want to start lining up forefinger in the direction of V and crawl towards the direction of B and look at which way your thumb is pointing. That's the direction of force on positive charge, okay? So here, this is positive charge, okay? So now, go ahead, use your right hand and choose answer here. Oh, I'm opening past time clicker question today. Okay, so yes, go ahead. And you have a minute to answer this question. Please practice, try it, okay? Oh, only 10 more seconds. Sorry I forgot to warn. 5 more seconds. 5, 4, 3, 2, 1, and it starts. Okay. Let's see how did we do. So mostly C, that says into the page. Yeah, that seems to be correct one. So how do we do it? So the problem is what you see on the screen versus what you see on the video may not be exactly same. So right now, mine are pointing in the direction of V and B. Black is in the direction of B, and this white is in the direction of B. Do you see same or it's reversed? I think it's reversed in the screen, right? So anyway, what you do is you start by pointing these 4 fingers in the direction of V and crawl towards B. So it's going to go that way. So if it is screen, then it's going to be to the screen. So it's pointing to the screen means into the screen. If it is pointing out from the screen or page, that's the out of the page. Okay, so that relatively went well. Okay. So if it was negatively charged, then the direction would have been exactly opposite, right? So now here is another question with the electron here. Okay, so electron is moving this way along the tube. Okay, and it says magnetic field point into the screen. So that means magnetic field is going to the screen, means like this. Let's say it's going like that. Think about these cross as the cross mark of the dart, right? So it's going into the screen. So direction of magnetic field, yes, it's hard to draw. So it's into the screen, okay? Not opposite of electron, but into the screen. So that's why it's drawn like that. Out of the screen, we just put the dot, means you see tip coming out. Cross means tail going in, okay? So that's that. So now I'll let you pull, and you have a minute to answer this one as well. And remember, this is electron, not positive charge, not proton. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So C, mostly up, mostly down, and some up as well. So only up and down, that's good, okay? But if this was positive charge, that would be up. But this being negative charge, we need to reverse that, whatever we get. So what happens? Your 4 fingers crawl that way towards the screen, okay? So when I, looks like, yeah, something like that. Towards the screen means towards you guys, okay? So when we do that, what happens? Huh. This is reverse, so unfortunately it doesn't work that way. But you wanna try like that, okay? So yes. So for me, what I'm seeing is, for me the electron is going that way in my screen, okay? And then when I do that, it's going up now. The thumb is pointing up. Now for the electron, it has to be down. So that's how I work, okay? And so, yes, so down is the correct answer, just like most of you identified. So to find magnitude, you do Q, B, B sine theta. To find direction, you use right-hand rule, okay? It's that. So that's that, folks. I think it's the end of class time. So feel free to, talk about it if you like. Otherwise, I'll see you in next class.
Thank you, Doctor.
Okay, thank you. Okay, bye-bye, everybody. I'm ending this meeting.